so answer this question, then I would be perhaps doing something like this, and you can always come back to these questions by adding, a little bit more to it, but use your time. What I wanted to do here and here, it would have been very easy for me to just put output final coordinates of type points. But notice I've also added image tilts and positions. So all of a sudden I've given in just a few words some extra information about my understanding of the output of the results. Here I've tried to add in a little bit more because I thought that it might be quite helpful if you say, again, I could have just put here analysis of results, and that would have shown me that you know the procedure, but if I put here, from a least squares solution, residuals on ground control, checkpoints, image residuals and variance, covariance, standard errors, all of a sudden you give me again a lot more knowledge, showing your understanding, and you basically only put a dozen words on the paper. So I can give you many more marks if you put all that, as opposed to just putting analysis of results. Try and be efficient with your words, but also try and add in little bits as you go along. If I was coming back to this, I would I've got a little bit of time. The other thing you could put in here on observed ground control is the ground control is normally round the edges of the block, isn't it? And then we have checkpoints in the middle. So there's no reason why even after you've answered all the questions, basically, you can come back, or if you've got enough time while you're doing it, just put another box in here and say ground control round edges to push any errors to the centre, where there would be checkpoints, ground checkpoints. Right, so again, that's sort of adding a lot more information about what you know without taking up too much time. I'm sorry, it's a bit scribbly on the board, but I wanted to write it fairly quickly to give you an idea of how, with a little bit of thought, you can add a few words in and gain more marks. Again, there's a bit more information you can put in on all these stages. This here, set up and solve the collinearity equations, if you had time. But time is going to be tight if if you get into one or two of the longer questions. All right? And of course, question 11, again, we'll come back to that a bit later on. But just sort of trying to give you a little bit of a feel for how to work some of these questions. Well, in fact, look, the fifth question here, he's actually saying, comment on the ground control requirement for the Ultronic. This is important, this ground control. It's so important that you can see, I could even believe I could even write a question expecting a long answer on this topic, because that is your quality control measures. Your quality control measures. How do you know you've met the specification? How do you know your results are good enough? Remember, at that aerial triangulation stage, we spoke about the fact that that's your first point in a mapping using photogrammetry when you have some quality check on the sort of results you're going to get. Develop the collinearity equations. What are these equations used for? The collinearity equations. I haven't gone into this as much as I have done in the past, so this question is perhaps not. I have gone into this. You can answer that part by just going through the computational or the derivation of the formulae, because it actually says develop the collinearity equations. That means show me how they're derived. What are these equations used for? I've essentially spoken to you about using them for aerial triangulation. Right? There are other uses for them, which would be the answer to that part of the question, but we haven't really covered that too much. If you look in the textbooks, you will find those answers. Well, actually, let me just jot them down over here, just so you've got an idea. So we've got them for the aerial triangulation. Tree. That is T-R-I-D. The second thing is, you know, when you those of you that did the practical exercise, and when we showed you in the demonstration that we've generated the stereo model is maintained in the software by real-time use of the collinearity equations. So the collinearity equations are continuously being solved, but only for 2 points, for 1 point and a point in the stereo model. So it can be used for stereo model viewing. The third thing it can be used for is something that we call space resection. And this is to find just the position and orientation of a photograph. So using 3 full ground control points. So in other words, we know the coordinates of 3 points on the ground, X, Y and Z, and we want to know the position where the photograph was taken and its orientation. Not a bundle adjustment, not an aerial triangulation, just a single photograph to find its position and attitude, and that's called something, a special name called space resection. And 4, there's something called space intersection, and this is to compute the stereo model coordinates from a pair of images where we know their position orientation, observations are the image coordinates. So in essence, you've got 2 photographs like this, stereo pair, you know where they were taken, you know their attitude, and you know the coordinates. You know the coordinates on the image, and therefore you're trying to determine that point, that stereo model coordinate. Right, so they are 4 things that we could say would answer that question, but just so that you've got a complete answer. Okay, whoops, where did we get to? This is this. So now I'm going too far. well, question 1 we did just now. Question 2, where would you distribute the ground control on a large block of aerial images? Sorry, I can see where this has come from now. It's obviously a derivative of the previous set of questions. Discuss the practical issues that need to be addressed when introducing GNSS and inertial measurement units into the aircraft. Right, these we spoke about. If we go back so that you can relate them to your notes, there was a whole series of slides here, and if you go through these, you can quickly see that we've got the issues that we need to address are the position of the antenna on the aircraft. We need to address the synchronization of the inertial unit, the GPS and the camera. We need to be able to address the issue of the tilt of the camera in relation to those components, those two other components. Remember we had a few slides here looking at the actual issues. We've got to be able to measure the lever arm, right? Measure the lever arm, haven't we? X, Y and Z. This is the tilt of the aircraft. We need to have some equations for introducing them into the aerial triangulation. We didn't do this in the practical or in the demonstration. The demonstration and the practical that you used did not use these equations. What they did was, what both those did was use the weighting of the initial values. The initial values that were input into the aerial triangulation. Right, so we didn't do these. We put in GPS, the inertial measurement values, into the aerial triangulation, having computed, effectively computed the lever arm relationship and applied that correction before we do the aerial triangulation. Right, so it's slightly different, but this is the way that is the general way of dealing with it. We put in some equations to deal with the GPS. If you remember, the other issue is the datum. We're going to work in GPS coordinates, which is WGS84. We need to transform to the map projection. And we could end up with some instability in the solution, which requires us to strengthen the geometry. And we need a rotation matrix, a misalignment rotation matrix, because we cannot bolt the inertial measurement unit onto the camera so that we know exactly the relationship. Because the gyros and the accelerometers for the inertial measurement unit are inside the box. And the outside of the box is not accurately made enough in relation to the gyros and the accelerometers to be able to bolt it directly to the camera and say they are aligned. So we measure them in situ. Right, so that's why that's a long question, that one, and it is a long question. There's a lot to talk about. If you've got, again, you're going to be time limited on some of these things. All right. Now the fourth question, discuss how a block of images can be geometrically strengthened by flight planning. Well, that's exactly what we were just talking about. I skipped over it a little bit. It's this here, look. That. I was talking about that. Do you remember these are the strips? And we put the control points in the corners. You can see the top one. We can strengthen the block, which normally has a 20% side lap, by having a bigger overlap. We can strengthen it by running height points, height control points along the ends of the strips, or even up the middle of the strip. Or we could actually fly the strips and then fly 2 cross strips or 3 cross strips, so that you've effectively got the photography crossing each other, and that would strengthen that weakness that you get with the photogrammetric images. Remember, the photogrammetric images are weak along the strip here, because when we overlap, they're strong down the strip, because you've got these triangles making up the frames, but here it's weak because you've got that small overlap between the strips, and of course they can flex. It's as simple as that. Strange that we're talking about these things, but in physical terms, but that shows in the mathematics. So it's the modelling, the mathematical modelling, where you can see these things occurring. Describe what measurements are required and how the measurements are made for aerial triangulation by independent models. Right, so I think I would, oops, sorry, I was looking for that diagram, it's the other way. I would actually draw something like this, I think. Don't forget you can draw pictures in exam questions. And then describe it, but don't just draw a picture and don't write anything about it, because that just says to me, oh, you've remembered the picture, but don't understand what's in it or what it's used for. So I would draw possibly a picture like this, and then I would talk about the fact that we need to observe these tie points. This is what the question's about. The tie points between the stereo models, and over here they've got to be in the lateral overlap. Right, so that's the essence of the question, and again it's going back to this issue of where you put the control points. So again, describe where you would put the control in that question. What measurements are required? Well, you need the X, Y and Z coordinates of the tie points. X, Y and Z, east, north, and right, whichever you want to call it, in the stereo model coordinate systems. So I think we've moved on to this one now. Collinearity equations. What are the collinearity equations? They are the equations that link, this is a short question, that link the perspective centre to the image point to the ground point. Those 3 points, if the photograph is in the correct position and orientation, should be in a straight line. Right? If the position or the orientation of the photograph is not correct, they will not be in a straight line. And it's all of the points simultaneously have to be collinear. List the variables. List the variables. So we've got omega, phi, kappa, x naught, y naught, z naught. And I would put rotations and position of each image. You could put I there to make it as though there are I images. What else have we got? We've got Z. I'm sorry, not ZA, I didn't mean that. We have got ZA, I didn't mean to put that first. I meant to put XA, YA, ZA. And here, I wouldn't use I because obviously that's the number of images. This is the number of type points or ground control points. Type points and ground control check points. Then we've got F. There would only be one F normally because the camera doesn't change during the flight. So there is F, which I'll accept focal length of the camera. There could also be additional parameters for camera calibration. Yep. And then you could also have in here now X and Y image coordinates. List the uses of the collinearity equations. We answered that question before. No, I'm sorry, I should have gone through. These three little groups of, or four groups of questions need a bit of reviewing, I think, to just remove the common questions. List the variables in the collinearity, which is what we've done there. List the uses, we did that back here. I'll show you. There they are. Why are the collinearity equations so important to photogrammetry? Because you've got those uses. Don't forget, I'll be perfectly honest with you, you're not going to get that question or that and that question on the same paper. They're too close. Alright? So don't expect, just because I put these lists of questions like this on one subject, that you get a whole list of questions like this on one subject. That won't happen. So you might get one of something that's about collinearity equations. You might not have anything about the collinearity equations. Derive the collinearity equations and define each parameter. Well, we've defined the parameters there. We haven't derived them, and I'm not going to do that on the board because I think you can go back through your notes. And of course, you have got the derivation in here. There. Let's make those a bit bigger. There you are. Fix those. Well, you don't need to do all those diagrams. You can probably do one. That. Well, those two slides are basically the solution. So a picture, something like that, and that would be the answer to that. Yeah, that's cool. I also clicked on something there. Don't want that either. Why have we got? It's not a big line there. Let's get rid of all that. Here it is. So we've got those three slides there that tell the story of the collinearity equations. All right, and there they are at the end. Got a few questions on satellite-based remote sensing after that one. Here we are. What is geometrical remote sensing? This is one of those little short questions. It's rectifying. Like that. Geometrical remote sensing is what I spoke to you about. It's trying to use the images that we get from remote sensing sensors on satellites primarily to produce maps. That's my definition, so I would stick with that. State 3 processes that can be considered part of image processing. If you remember, we spoke about the processes, the broader, more general processes of remote sensing, and of course that involved image processing where you can manipulate the image. Right? You can contrast, stretch it, you can change the spectral bands, you can do analysis of different spectral bands within the images, and so on. So there are several processes, and that's again listed on one of your slides. What processes are involved in image rectification and restoration? And this is now, in fact, that question and the one after it are almost, that's giving you almost the answer there. The processes involved in image rectification are that we need some ground control points, and then we need a transformation, and the transformation that is normally used is a polynomial transformation. And the polynomial transformation, if you remember, provides you with a form of rubber mat, where if you've got your, that's a good example, look, if we've got an image on a piece of, on a rubber mat, and we stretched it to fit the control points, like that, and obviously if I had multiple hands to put on the control points, and that would then stretch the image to fit on those points. Clearly, where you are not fitting to the points, where you haven't got that close control point, the image is just being linearly stretched according to the polynomial that you're using. So that's the basis for I suppose, the answer to question 4. Discuss the use of radiometric correction and why it is so important. This question is probably not quite so relevant now. We used to do a bit more on remote sensing, where we used to do a bit more on image processing and manipulation of the image. Radiometric corrections are to do with the calibration of the spectral bands that you can record. And once you've captured the image, you can then calibrate it to actually give you the purer spectral bands. One could also call it radiometric correction when you actually go out in the field with a spectrometer and you record the spectral response, literally with a spectrometer looking at the ground, of that spectral band that the ground surface is reflecting, and then when you get the remote sensing image, you can go into that image and you can say everything that's of this spectral band, let's call it a colour, like blue, everything that's blue, you can recalibrate it or recorrect it by applying a correction to make it a different colour that's based on the colour that you picked up on the spectrometer in the field. So it's really more to do with not the geometric correction but the but the image, what the image looks like in terms of its colour. Question 6, describe the geometry of the Spot satellite scanner system. Long question. If you remember, this is very, very similar to the ADS-40, the airborne camera or scanner. And if you remember, both of them work by having a single pixel wide but many pixels long sensor. It's got a lens system, so you're still getting perspective geometry across the strip, and it records just a strip of the ground surface. The aircraft moves forward, or the satellite moves forward. As it moves forward, it then takes another picture which overlaps a little bit with the first lot of pixels, and so on until you build up an image as the aircraft moves forward. Each of these bands is captured. Satellites are the traditional way of recording this type of push broom. Remember, push broom scanner? Just think of a broom. It looks just like that. You've got a wide head to the broom, and you've got a broom handle that's actually you could think of as the focal length of the lens system, and you're just pushing it along, and you're picking up the image as it goes. You've got several diagrams and pictures in the notes on the Spot system, but if you look back at the ADS-40, you've got something very, very similar coming up there. Digital surface models. What is a digital terrain model? This is a series of spot heights over the landscape, recording the height of the terrain being the ground surface. All right, remember that the terrain is the ground surface rather than the what's on the surface. What are the limitations of a regular grid digital surface model? It's a short question. I could probably have said, what are 3 limitations or something like that, 2 limitations, but I've left it a little bit open here. I suppose the biggest limitation is what grid interval that you use to best define the landscape where you're working. Do you have a 50-metre grid interval, or do you have a 10-metre grid interval, or do you have a 1-metre grid interval, or 5-centimetre grid interval? Because the bigger the grid interval, the less data that you're going to collect. So from an efficiency point of view, from a processing point of view, it's an advantage. But, of course, fine detail will fall inside the grid, right? And you won't capture it, you lose it. So the limitations are the grid size, the limitations also are that they are normally interpolated from a more random distribution of points. If you think of a laser scanner or even a digital surface model captured by photogrammetry, the laser scanner is pumping out laser shots, capturing them back and recording where they are. It's not picking up a point on the grid. Photogrammetry, when you do the image matching to get the digital surface model, it is not picking up a point on the grid. It's again picking up object points and then you interpolate. So a grid, whilst looking very good, looking very helpful, can sometimes be from an interpolated model. Describe 2 methods of airborne laser scanning ground patterns. In other words, if you remember, I drew a series of pictures on the board, and you can get a scanner that goes round and round like this as the aircraft goes forward. Here's the aircraft going forward here. It could be a mirror that's doing this. So you're getting a zigzag. You can get one that's coming crosswise in lines like that. It just depends on the sensor head. And you can obviously, the other one I was thinking of is that you can get them where there's a whole series of lasers being projected out to get a, if you like, almost more of a push broom scanner kind of system where it shoots the lasers downwards, a line of lasers and then another line. I'll tell you where you see something similar to this. Highway engineers use them a lot on their rolling road maintenance equipment. They quite often have a trailer, and on the trailer is the wheels either side being towed behind a vehicle, and they have a line of vertical lasers, and the lasers record, and they get a profile of the road surface. Profile of a road surface. Profile of a road surface. Right, so this is the similar sort of thing. It's profiling the road as it goes along. Boom, line of points, boom, next point, boom, next lot of points. This is because, those of you obviously that are engineers, this is for rutting. Normally, you know, you find that road surfaces eventually you end up finding where the vehicles will travel, when the roads start producing ruts, particularly heavy goods vehicles can cause those problems. But that's if you like, a non-airborne version of the laser scanners. But again, look at the pictures, and there are several that you can choose from there. Describe how an airborne laser scanning system works. And this again is really one of the slides that you've got to save me going through all the details on the board. You'll find that, I think it's in here. This is quite heavy. Here we are coming up. Oh, there's the one that we were just talking about. And here's the picture that I would suggest you would draw and describe for the answer for that. How does an airborne system work? The second discuss the sources of error in airborne laser scanning. And if we go back to that same presentation, oh, there it is. There's the sources of error. Discuss the sources of error. So some of the questions are, you know, almost directly off the slides. Obviously, if you can add in a bit more information, so much the better. And the final question there was to do with describe full waveform laser scanning and what potential benefits does it have. Well, there's the full waveform scanning, and the potential benefits are that it gives you some idea, particularly with vegetation, what type of vegetation it is, and the condition of the vegetation, and the height and the density of the vegetation. So it's trying to analyse what you can get from the laser scanner echoes in terms of the characteristics of the vegetation. So, that leads us, whoops, wrong slides. That leads us on to the last lot. What is camera calibration? Camera calibration is the process of determining the internal geometric characteristics of the camera. Right, if you want the definition. It's the internal characteristics of the camera. Determining the internal characteristics. Why is camera calibration so important in close range photogrammetry? It's important in close range photogrammetry. Because often the objects take up a large depth of field that you're observing or you're recording. All right, a large depth of field. And if you draw something on a piece of paper and look at the sensitivity of the geometry of a camera in relation to a large depth of field, then you find that it is more sensitive when you get a large object covering a large proportion of the depth at which you're working. When we work with airborne photography, or even more so satellite photography, the landscape is very small compared with the flying object. And it means that when you're measuring in this space here, it's not quite so sensitive to the camera geometry up there. And a small change in the camera geometry up here doesn't have much effect on the measurements in that stereo model. But if that is very large and we're up here, then a small change on that large area makes a lot of difference. There is another issue with camera calibration that relates to not so much the large depth of field, but with airborne cameras, it doesn't really matter at the end of the day where the position of the camera is, because it could be higher or it could be lower if the depth of field is very small. It doesn't really matter what's happening up here. But if you put GPS on the aircraft, it does start to affect the calibration. We haven't had a chance to talk about this very much, but you then stop the aircraft moving up and down due to the focal length being incorrect, and it locks it, and it then pushes the errors down to the ground surface. And you can start then getting problems with fitting on your ground control, because the aircraft and the internal geometry of the camera is actually pushing the errors down onto the stereo model or onto what's in effect the ground surface. So that's really number two, and I've expanded that to just talk about the airborne there a little bit. What are additional parameters? Well,
so about the second question, how about oblique cameras?
Yeah.
Is it important, like calibration would be very important then?
Yeah, oblique photography is actually not easy to work with. It's actually quite difficult to work with because the calibration does have to be very good, but if you've got an oblique camera like this, so this is where the camera is intentionally tilted, and you then start to have that sort of situation occurring over here, you've obviously got a large differential range between that and that. And what can happen, and this is more to do also with the aerial triangulation, a very small tilt error can cause that to come up a long way or go down. And you find that really you end up with defining a working area that's a lot smaller than the total. And it is very difficult to control that, because the further it goes away, the more difficult it is to get accurate measurements on this surface or these target points. So it is not particularly easy. I mean, it's okay if you're going to work just within this sort of vicinity, but when you try and work with the whole range, it becomes a bit more challenging. What is the point of autocollimation? Oh, this does really probe the thoughts. If you remember, we spoke about the point of autocollimation, and it goes back to what we define as the principal point. In a perfect camera, then we have a lens system like this, and this ray coming from infinity through the camera, through the lens, would hit the focal plane at right angles, like that. And that would be what we would say is the definition of the principal point. And it would also be the principal point, or the point of autocollimation. Now, in a real camera, that doesn't quite happen in that way. What we get is that the rays coming from infinity. That's it. The rays coming from infinity, if they were coming in perpendicular, like this, perpendicular to the focal plane, so that would be, this is showing that it's a right angle, like this little box here. This is a right angle here. Then the real camera would cause a deviation of the rays coming through here potentially, and you would end up with them coming through like this and focusing just there. Now we've got a situation where these rays are coming in, they're perpendicular to that focal plane. The ideal camera is letting the ray come through the middle and striking it just here, so that's perpendicular. Here, we haven't got that. That chief ray has come through the lens, and that is not 90 degrees. These are 90 degrees to that. So they are coming in at 90 degrees to that, but that is focusing on a different point. You see the subtlety and the difference? Alright, perfect camera comes through focus. That is where the principal point is. On the real camera, they come through and they focus somewhere else, even though they're coming in perpendicular to the focal plane. This chief ray here is not 90 degrees. That is the point of autocollimation. And that is the point that is normally considered as the best estimate for the principal point. Okay? The best estimated position of what we consider to be the principal point. And then the last question, discuss the geometry of a real camera and how it relates to perspective geometry. Well, this goes back to really this slide here. I think, again, keeping half an eye on the clock so we're not here till midnight. There we are. Let's go right to the end here. Here it is. That's the one. This is the diagram that you need to draw. You need to draw this, and you need to talk about the ideal camera and the fact that the value of f, no matter what angle you come in at, the measured radius divided by the tan of the angle is going to be a constant. So if you were to draw a graph of the radial distance compared with f, you would end up with a graph that looks like that. F would be a constant, and this is the radius. Radial distance is equal. Distance like that from the centre going that way and that way. If it is not a constant, then that value of f will change as you change radius, and the typical sort of shape you would get is something that looks like that. And it looks like that purely because when they make lenses like that, they grind the lens. Sorry, it should have been equal there, shouldn't it? Equal on each side. That's the cross section through it. So it's circular here. When they make the lens, they grind and they polish in circles around the lens like that. And it tends to cause a distortion like that. Your camera in your smartphone will look like that. The photogrammetric camera that you buy as a photogrammetric camera will be close to that. Close. It will probably be something a little bit more like, perhaps, like that. Very shallow, but nearly flat. Okay. I think we've got to the end of the questions now. So, has anybody got any questions on that at the moment? Okay, let's have a 10-minute break. And then we'll come back and we do the 3 exams.